But before that, we can also discuss some circuits so that you people can do some assignments as well. So recording has started, and then I will go to my uh, writing pad, and then I will open up a new one. And then, so in the earlier sessions, we had discussed some op-amp schemes, some op-amp circuits. I will revisit some of that quickly, and uh, then build on the top of that to come up with some versatile op-amp scheme which are popularly used. So let me start with a simple differential amplifier or a diff-amp circuit. You have already covered different kinds of differential amplifiers with different active loads. So some of that I'm drawing just for a recap. So the simplest differential amplifier that all of you have seen is differential amplifier with a resistive load. So what is the gain of this? M1, M2, M3. Small signal gain of this. This is your VO plus, this is your VO minus. So what is the gain? Yes, quickly, what is the gain? Here the gain AV, I will define it as VO plus minus VO minus divided by V, I can call it VI plus VI minus. So VI plus minus VI minus. So this is a small signal gain. What is the small signal gain of this circuit?
GMRD.
GMRD.
GMRD, right? So this is GMRD. Anybody having any problem with this? You know how to define the gain, right? The half circuit, common mode half circuit, and the differential half circuit, assuming that all the parts are perfectly matched. The M1, M2 is matched, RD1, RD2 is perfectly matched. This is the small signal gain. But of course, in real circuits, you might have done experiments in your lab also with real components, and you will see that you will never get exactly matching RD1, RD2. You will never get exactly matching M1, M2. VT will be different, and there you have to adjust the gate voltage to get the same DC at the output. That happens, right? All of you have seen that in your lab.
Yes. Yes, sir.
So if I assume everything is perfectly matched, then output DC will be same. But if any one of them is having mismatch, MOSFETs are having mismatch or resistors are having mismatch, then you can obviously expect that the output DC will not be same. And then you need to adjust the gate voltage of the one of the MOSFETs so that the output DC becomes equal. So now in this circuit, if you have to just recap, you assume that this is an AC ground, and then you can put it as a common source, and then this is GM1, and this is RD, and this is VI plus. Now VI plus, you can always assume that you have a common mode signal and differential signal. Common mode signal, you have seen what is the common mode in this? VI plus VI minus by 2, right? And the V differential is VI plus minus VI minus by 2. And then based on that, you can simulate the common mode and the differential signal. And the single half, if I assume the differential signal like this, so this is the VD plus. The VD plus and VD minus will be just the reverse of this. And how do you assume that it is correct? So you just add the whole thing up, and you should get the overall signal. So if you add a VD and CM, the differential signal VCM plus the differential signal, you get the on two sides you will get the same signal. So VD plus VD minus will be VI minus minus VI plus by 2. And on the other side, if you sum it up, you will get the same signal. So here we get a single-sided gain of this is GM1 RD times the VD by 2. And the other side also you will get, of course, here it will be a negative sign. And other side also you will get the same thing. And then you add it up and you get overall GMRD. And the common mode half circuit also you might have studied. I'm not repeating everything. These are basic things that you should remember. The common mode half circuit, you have this AC ground, the gate of the M3 is AC ground. And the common mode half circuit, you can combine the two. So this becomes RD by 2, and this becomes 2 GM because you have joined the two MOSFETs and you are applying the VCM over here. And then you can find out the common mode gain at the output. There is a common source amplifier, which is source degeneration, where the degeneration resistor is RO3, right? So this also you can find out. So these things you have done, and it's not a big deal. Likewise, if I look at the input, what is the problem with this resistive load? Why do we go for active load at all? Why do we go for active load at all? Why? What is the problem with RD? Yes, anyone?
Sir, we want to keep the same gain by increasing the swing, right? Because since we have an RD here, the voltage here will be VDD minus of ID times RD in the voltage, the DC voltage that is at this point. But however, if I use a PMOS at active load at this point, then I can increase the voltage swing.
Yes, we increase the voltage gain, but here also we can increase the voltage gain by increasing RD, right?
The swing, sir, voltage swing.
Okay. So here what he's saying is that if you have to increase the gain in this case, so you have two options, GM and RD. So either you increase GM or you increase RD in order to improve the gain. So how would you increase GM? So GM in this case, you can increase by changing the W by L, or you have to increase W by L, or you have to increase the I bias. These are the two ways. So if you one option is that you go on increasing the W by L. If you just go on increasing the W by L, you may be able to improve the gain. It is a square root dependence, but that will consume a lot of power, right? So just increasing the W by L of the input devices will go on increasing the capacitors. The For the W by L increase, it will lead to increase in parasitic capacitance, and it will slow down the circuit. And if you just rely on IB, that is going to have effect on the power consumption as well as output DC point. So now if I assume that I'm only relying on W by L, so you know that the GM is proportional to root W by L, and the DC point is mainly decided by the I bias and the RD. So that is anyway fixed in this case, and you just go on increasing the W by L. So in order to get the gain increased by 4 times, you have to 16 times increase in the W by L of the input device. And that is going to further, 16 times degrade the bandwidth, right? Because capacitance are directly proportional to the W by L. So if you are increasing this by a factor of K, the bandwidth will reduce by a factor of K, and the gain will increase by a factor of root K. So it's not a good trade-off. Your bandwidth is going to drop. And if you just rely on I, so you have to increase the I. In that case, once again, the DC point will keep shifting down because the RD1 is going to create larger DC drop, and proportional to the ID, the DC point will be shifting down. Now the gain is only increasing by root ID, but now the DC point is dropping proportionally, right? It is directly linearly proportionally, it is dropping. So in order to have a output DC point properly set, what is the condition? Generally, we try to set it for the maximum symmetric swing. So I hope you remember this discussion from your analog circuits. What is the condition for maximum symmetric swing that we have in this circuit? How do we find out the maximum symmetric swing condition? These things means you have in some of my lectures, recorded lectures, I have already covered. So do I need to cover all these basic things, or you already covered in your recorded lectures? Can anybody suggest? Anybody who feels like, yeah, we need to cover, I will be happy to cover. If you feel some of these things are repetitive and have been already given in some of the recorded lectures, I will skip some of the basic things and go to the next steps. Yes, any comments? Nobody has any comment. The swing, etc., symmetric swing and all that has been covered earlier. in some recorded lectures? Are you people
sir, it
understanding
was-
anything? Yes, hello?
Yes, sir, it was there. Yes, sir, it was there. You have discussed in one of the lectures in NPTEL.
Anybody else thinks that I should cover this? You can tell me right now. Yes, anybody? Quickly. Remember that very soon I will start taking tests also daily basis. So you need to be, aware of the concept that are being covered. So there will be MCQ tests based on whatever is covered in the sessions. Yes, anybody? So let me ask someone rather than asking me that way. Let me just try to assess. Some people have run away. The moment I say that, I will assess. Some people ran away. So anyway, so let me. Harsh Raj, can you unmute yourself? Harsh Raj, am I audible? Harsh Raj is not even listening. Okay. Abhiraj Ranjan, can you unmute yourself? Abhiraj Ranjan. I think these people are just coming online and sleeping. Abhiraj Ranjan. No reply. Jishnudeep Patra, can you unmute yourself? Jishnudeep Patra.
Yes, sir.
Okay, finally. So 33% of people are listening, it seems. Anshuman Maiti, can you unmute yourself?
Yes, sir.
Some people are coming just for attendance and they are, sleeping. Anyway, so who said yes, sir, first? Jishnudeep Patra, right? Jishnudeep Patra?
Sir, can you hear me?
Yes, yes, but you wait. First one, who was it? Jishnudeep Patra? Jishnudeep Patra,
sir,
are you
yes,
able
sir.
to hear me?
Hello, sir. Yes, sir.
Okay, so answer this question. That what is the condition? How do you obtain the condition for maximum symmetric swing in this circuit? RD, GM, some ID bias is there. So what is the consideration for maximum symmetric swing? How do we arrive at this?
So maximum symmetric swing for this differential one.
Yes, output. So what are the considerations? So given, suppose you are
Sir,
given the value of
the highest output is VDD, and the minimum point it can go is
VG, so suppose VGCM, common mode voltage is VGCM.
Minimum point it can go is VGS minus VT. I mean, and VS is again VS can again go about up to for ID for the M3 one. For overdrive voltage of the M3 maximum one. So
Yeah, so tell me, so M3, suppose 1, 2, and 3. So what is the VGCM that I should put for maximum symmetric swing?
the VDD minus VGS minus VT by 2. VDD plus VGS
Suppose
minus
this is
VT by 2.
VG3. So for VG3, suppose I give you the number VG3. So as compared
Yes.
now, can you tell me?
So VS can be VS is VG.
What is V out mean in this
Minus-
in terms of variables given here? What is V out mean?
V out mean is VGCM minus. I mean VGCM minus VS is VG3 minus VT3.
So VT3, what is VT3 coming into picture? So VGCM is given with respect to VGCM. What is the minimum voltage you can have at the output?
Minimum voltage.
Not clear. Basic things are not coming. So I'm a little worried. You know, whatever I'm going on teaching, you know. Amresh Kumar De, can you unmute yourself? Amresh Kumar De. Another sleeping person. Yes, did you hear the question? Amresh Kumar De. Yes, is the question clear to you? I'm not able to hear you. Yes, hello, Amresh. I don't know what is going on. Amresh, is your audio clear? Ishita Mishra? Ishita Mishra?
Yes, sir.
Yes, can you answer the question?
Sir, V out minimum should be VGCM minus VG3 minus VT2.
VGCM minus what?
VGCM minus the source voltage at the MOSFET of MOSFET number 3. So for that to be turned on,
Source voltage of MOSFET 3.
so it's a drain voltage.
Suppose the VGCM is given to you, some value for which the MOSFETs are on. Now, what is the minimum value at the output DC? What is the condition for saturation region for MOSFET and MOSFET?
Sir, the VD should be greater than VG minus VT of the MOSFET.
Then what is the problem? Why are you not giving the answer? What is the minimum drain voltage for M1?
So the minimum drain voltage will be the gate voltage minus the VT of 2. So VGCM minus VT2.
VGTM minus VT, assume they all have same VT. So this is the V out min. And therefore, first thing is we need to get the maximum symmetric swing. So how do you maximize the swing? Is this clear to everyone? Because if the gate voltage for the M1 is VGCM, the DC voltage, assuming that the input signal swing is very small, I'm ignoring any change in the input gate voltage, which is an approximation. Assuming that the input signal is small, I'm checking with respect to the input DC level. With respect to the input DC level, what is the minimum drain voltage M1 can have? Because when the signal is applied, ultimately the drains of M1 and M2 will keep going up and down. Upper side maximum, it can go to VDD. Lower side, how much it can go minimum? It will be given by VG minus VT, right? That we have VGS minus VDS. So we know that for NMOS, for saturation region operation, VDS should be greater than VGS minus VT. And then the source is same, so we just cancel out and then we just say VD greater than VG minus VT. If these things you're not able to answer, then I don't know how you're going to design circuits. So in this case, the output minimum should be VGCM minus VT. So in order to maximize, this is the maximum voltage and minimum voltage. So the output signal, it can go maximum to VDD, it can go minimum to, this can go minimum maximum to VDD, lower side, it can go minimum to VGCM minus VT. This is the min voltage and this is the max voltage. Now, first thing is you have to go for symmetric swing and maximum symmetric swing. There are two parts. First thing is you need to have maximum symmetric swing. You need to have maximum swing, and then that swing should be symmetric. That means the upper side it should have same room as on the lower side. So how to first of all maximize the swing? So in this case, max value is anyway fixed. The minimum value is this. How will you maximize the swing?
So the lowest value of VGCM should be such that the MOSFET 3 is turned on.
MOSFET 3 is turned on. Who will decide whether MOSFET 3 is turned on?
So like the VDS of MOSFET 3 should satisfy saturation condition.
So what is the VDS3 min? This is VG3 minus VT, right?
Yes, sir.
And then that gives us the VGCM min. What is VGCM min? This is VDS3 min, that means VG3 minus VT plus VGS, because the VGS is anyway decided by the current that you are having and the W by L, right? So this is the VGCM min. So now one is a fixed parameter VT, and there are two parameters VG3 and VGS1. So how can we minimize VGCM min? What does it depend upon? If you have to maximize output swing, you need to lower the input DC voltage. And for that, I have VG3 and VGS1. If I reduce this to the minimum possible value, then the output swing will be maximized. How do I reduce it? VG3 and VGS1 for a given bias current IV.
So we can increase the W by
Increase the
L.
W by L. So the input device W by L and the lower device M3 W by L. If you increase, then the VG3 will go down, VGS1 will go down. As a result, you will get lower and lower VGCM. But then there will be a limitation if you go on increasing. Again, there is some benefit because your GM is increasing. GM is proportional to root W by L of M1 and M2. Gain is improving, but your capacitance, the parasitic capacitance will be also increasing, and that will slow down the circuit. So there is always going to be some trade-off between the gain and bandwidth. So okay, fine. So we did that. We tried to obtain the VG3 and VGS1. We tried to increase the W by L so that this can be lowered to certain value. After that, how do we design it for symmetric swing? So once we have some maximum, certain maximum swing, how do we go for, symmetric swing? Yes, anybody quickly, let me, these are basic calculations that you should be aware of. Abhirup Das?
Yes,
Abhirup
sir.
Das? Yes, can you answer? What
So
decides the symmetric swing?
For maximum symmetric swing, the input voltage should be V out max plus V out average will be V out max plus V out mean by 2. The input voltage VGCM.
Sorry, once again.
Like the swing should be around V out max plus V out mean by 2.
So the DC voltage V out DC should be equal to V out or V out max plus V out min by 2, right? It should be the midway. So whatever is the V out max and V out min by 2. So what is that value? That value is equal to VDD minus I bias times RD. So if your I bias is fixed, RD is a variable. You can set the RD such that this condition is satisfied. Is that clear to everyone?
Yes, sir.
Yes, sir.
So now here there is a trade-off. Like if you want to increase the gain, your swing is going to be dependent upon the RD. So if you have to increase the gain, Once you have increased the W by L of the input devices, you increase the gain but reduce the bandwidth by even bigger factor. And then your R is also creating a bottleneck for the swing, because as you increase the bias current for improving gain, the DC swing will, sorry, the signal swing at the output will reduce, because the DC point will shift towards lower value. Now, if you increase R, the same thing will happen. For a given bias current, you can increase R, but that will also proportionally reduce the swing. It will push the DC value downward, so it will reduce the swing towards the lower side. So this is one of the main reasons why we don't use resistor values and differential amplifier, the resistive load, right? And there are other issues also, like if you want to uh, do the layout in terms of area, resistors take good amount of space. So in terms of area also, it is not very efficient, because MOSFETs take much lesser space than the resistor. So area penalty is also significant. Area of R will be generally significantly bigger than area of MOS. So area point of view doesn't, it's not very efficient to use resistors everywhere in the differential amplifiers. And there are some other concerns also related to noise. So noise point of view, the resistors also contribute to good amount of thermal noise. So that can also be an important concern. But major two concerns are these, in terms of the swing, there is a trade-off between, swing, gain, bandwidth. So there is a trade-off between these, a very strong trade-off. And in terms of area, it is not very efficient. So then we go for active devices, active load. So active load point of view, you have seen several kinds of active loads, right? So this also you have seen. This is one case. This is your second case. And this is your third case. All these three schemes you have seen, all of you have seen. Anyone who has not, seen all these three cases? Yes, anybody who has not seen all these three cases? There is no hesitation. Means if you have not seen it, you can just speak out that you have not analyzed all these three cases. Anybody who has not analyzed these three cases? So let me ask. If you don't reply, then I'll have to ask. I'm assuming that
Sir.
everybody has. Yes.
Sir, the first one.
The first one. What is the problem with the first one? What is the small signal half circuit of this one? AC half circuit. What is the AC half circuit? Yes, tell me. What is the half circuit? Differential half circuit. I need answers. You just can't sit mum in the class.
So the common source becomes the ground. That is the lowermost MOSFET, we can remove it and we can ground it. And the uppermost MOS is direct connected.
What is
the gain?
What is the gain?
Sir, GM1 by GM2. GM1, approximately GM1 by GM2. Yes.
So this is the single-sided gain, and both sided, if you combine, you will get the same. So V out plus minus V out minus divided by V in plus minus V in minus. This is the gain, GM1 by GM2. Everybody is understanding this? This is very clear. It's common source amplifier with diode connected load. Anybody has doubt on this? These things are, I hope you understand, right? Anybody not clear with this? Yes, hello. What is the gain of the second one? Second one?
Sir,
Differential gain of the
GM1
second.
into RO1. GM1 into RO1 parallel RO2.
Yes, because it's a half circuit of this one is just like, common source amplifier with active load, and the gain is GM1, RO1 parallel RO2. Third one. Third one, what is the gain? Yes. Yes, anybody? How do we calculate the gain of the third one?
Sir, it should also be GM1 R1 parallel R2.
GM1, RO1. Here, how do we calculate the gain?
Sir.
So rather than going for the half circuit, in this case, because the circuit is at the load side, it is slightly asymmetric. So in terms of calculating the small signal gain, one easy method is that we assume that this point is AC ground. So you can put a AC ground over here, and then assume that you are having differential inputs. Fully differential input is being applied. You have VG plus VG by 2 minus VG by 2, right? So VG is the differential input. So any input you can break it down to differential and common mode. So the differential input, suppose it is VG. I have broken it down VG by 2 minus VG by 2. Overall, it is VG. So the differential input applied to this amplifier is VG. And then because of this, how do we calculate the net gain? So now assume that this is AC ground. The first one is M1, second is M2. So first one will give you GM1 VG by 2, GM VGS, small signal current. Same current flows here. And the second one is going to give you minus GM1. Again, GM1 is equal to GM2, match transistor. So minus GM1 VG by 2. And in the upper two MOSFET.
GM1 VG by 2.
Sorry?
So from the top one will mimic the current, right? GM1 VG by 2.
Yeah, so this
Since
is
it's the
mirror.
diode connected.
So this is a mirror. So this is M3 and M4. M3, M4 are forming mirror. So here you have M4 going to mirror the current of M3. Small signal current will be mirrored. It is mirroring the DC current also, but along with that, it is also going to mirror the small signal current. So whatever small signal current you are going to get minus GM VG by 2, it will be mirrored here. So here it will be GM1 VG by 2. And as a result, here, if I look at the output node, if I have the net small signal resistance over here, which is equal to how much? If I assume that this is AC ground, the small signal resistance net value over here is what? RO up parallel RO down. So the R out here, this RO is RO in this case is RO4 parallel RO2, right? Whatever we call it. So this net current flows into this. So what is that net current? Ultimately, it is minus GM1 VG by 2 is downward, and GM1 VG by 2 is in this, it is flowing this direction, and minus GM1 VG2 this direction. If I just reverse the sign, I can reverse the direction also. If I make it plus, I can just reverse the arrow. So then this net current going into the output resistance, RO1 parallel, RO4 parallel RO2 becomes V out AC
GM.
signal is GM1 times this becomes double. So GM1 VG into RO4 parallel RO2. If I assume that both the ROs are similar or same, I can just put it RO by 2, and therefore you get GM1 RO by 2 times the differential signal, which is VG. Is that clear? So this is one way of looking at the third topology. And because of the similar reason, we also say that the third topology. So what is the difference? The fundamental difference between the third and the first two is what? Fundamental difference between the operation of the first two and the last one is what?
The first two are the differential
outputs.
Sorry?
So the first one is differential to differential amplifier. That is, it takes in differential input and gives a differential output. The first two, and the last one gives a differential input and takes a gives a single input output.
Yes. So the first two are fully differential output. So we are taking the output also fully differentially. But the third one, the output is single-ended. Input is differential, but output is single-ended. What is the problem? Like, what any disadvantage of doing that? Any disadvantage of the third scheme?
Source loss doesn't make.
So the first two schemes, if the devices are completely matched, perfectly matched, what is the common mode gain? If I assume that the common mode gain is defined as differential signal, output differential signal coming because of the applied common mode signal. Generally, if you look at textbooks, they will define the common mode gain for the first two cases as either of these two outputs, right? So they will assume the signal at these two outputs, and they are going to behave in the same way. If the input is symmetric, or sorry, the devices are symmetric and fully matched, you will get, and if you're applying the common mode signal, same signal at both of them, output will also have the same effect, right? Both outputs will have exactly the same effect. So ideally, if the devices are perfectly matched, the first two cases, common mode signal will not appear at the output. It is ideally going to have infinite CMRR, common mode ratio, common mode rejection ratio will be infinite. For ideal case, when you don't have any mismatch. Is that clear? Because you're taking, if you're assuming that the common mode gain is defined as differential output divided by the common mode signal. Differential output will always cancel out the common mode gain. If you define the output as either of these two, then you have finite common mode gain. Because in textbook, they will define only one of the sides. So, if this is your VO plus, they will define VO plus divided by V in CM. Then you will get finite common mode gain. But honestly speaking, the true justice is you look at the output voltage, VO plus minus VO minus divided by V in CM. Because of any common mode signal appearing at both the inputs, what is the differential output? Ideally, it will be 0. Is that clear?
Yes, sir.
Now, under what condition? So, so for fully differential circuits where you have noise sensitive signals, you have VDD noise, you have some common mode noises like noise coming from digital circuits, clocking circuits, this and that, substrate noise. So there are a lot of different sources of common mode noises in the chip. And if you have analog signals which are sensitive and you are trying to design something very high resolution, you want to very accurately capture the analog signals, then it will be better to go for fully differential topology because they will reject the common mode noise at every stage fully, provided they are very well matched, assuming that the devices are well matched. But if the devices are not well matched, then what happens? If the devices are not well matched, what happens?
There will be some gain in the voltage. The common mode gain will be there due to the unmatching.
Yeah, because now the half circuits are not symmetric, right? So simply, if I again take a crude assumption that still I assume that point as a common source, the common source point, if I assume it as AC ground, in this case, it is going to be an simplification because if your two devices are asymmetric, you may not have exactly AC ground. Other option is that if there are two sources of mismatch in the first circuit, right? You have the input devices also and the load devices also. So if the resistor itself is mismatched, and assuming you can ignore the lambda, then you can still assume common, the source point to be AC ground. So if I assume that this is RD and this is, RD plus delta R, RD, and then my input devices are supposed perfectly matched, and I have certain voltage, the DC voltage is VCM, VCM. Now, in terms of DC bias, if I ignore the lambda effect, the channel and modulation, then I still get whatever IB by 2 you have, I still get IB by 2, IB by 2. So the GM is still similar. GM is still close. GM1 is equal to GM2, approximately. but the output DC point is going to be different because one side you have delta RD and the two sides. If I assume that this is half circuit common group, this point is ground, and the net gain on the two branches will be also different, right? So although you are having a common mode signal. So if you are applying a common mode signal, what will be the common mode half circuit looking like? So in the common mode half circuit, you are having VCM applied to both the signals. So now I have to split it into two halves. And in order to do that, I will take the source transistor, the current source transistor, I can make it half and assign it to the two sides.
So like we'll be halving the width, right, of the lowermost transistor.
No, here I have just broken. So here I am dividing this, the tail transistor into the two, equal parts. So now this is RD plus delta RD, and this input devices are this is same W by L, M1, M2. So these two are same. But now if I look at the overall common mode gain of these two, you will get a output term here for the same VCM. You will get an output term delta RD times GM. So although this is still source regenerated, but there is a delta RD term coming, and as a result, this guy will give you something like GM RD plus delta RD upon 1 plus GM RO, GM 1 times RO of 3. And the other guy will not give you delta RD. The difference will be like this. So you will get, the differential, this will lead to a differential signal basically. So AD coming from the common mode signal. So you are getting a differential signal by applying a common mode signal. So although you have applied the same common mode signal to both the inputs, because of a small change in the resistance, one side you have delta RD 10% different. So that 10% difference will lead to 10% signal transfer. The common mode signal will get transferred to a differential signal. So on both sides, you are getting effectively a difference. So what does it mean? That even if your common mode signal is fluctuating, in case you are interested in only the differential signal, but your common mode signal is also fluctuating. So this is your differential signal, input signal. We want to reject the common mode noise. We are only looking at the difference. Got deleted. So because of some reason, the common mode can shift. Suppose the differential signal is what is of interest. So again, it gets deleted somehow. Some strange things happen with this tool. So in this case, this is the envelope of this is the common mode signal. The common mode signal is changing like this. Differential signal peak to peak is remaining same. I am not interested in this common mode swing. I want to reject it. It is because of some external disturbance, because of maybe shift in the input DC. My interest signal is the differential signal. I only want to pass this. But now, because of this non-zero common mode signal, I'm going to get a differential signal. The output will get superimposed. This will produce a differential output which will get superimposed on the actual differential signal, which is not desirable. Actual differential signal is only this much. But now, this guy, because of this change in the RD, this is going to lead to an effective increase in the or decrease in the common the differential signal based on the polarity. So now my output side, you will get some corruption. Is that clear? Because the common mode signal is now getting converted into differential signal. That differential signal at the output will get added to the actual differential signal and will corrupt the value. Is that clear to you, all of you? Same thing will happen if your MOSFETs have difference. That will be even more pronounced because MOSFETs, the GM will be differing, and GM will also lead to similar change. Delta GM will be there, and the delta GM VGS will give you a differential signal. So the moment the transistors are mismatched, resistors are mismatched, even if you apply a common mode signal, it will generate a differential signal at the output. Have you done any simulation like this or any circuit simulations in your lab to demonstrate this difference? The common mode to differential transfer or common mode to differential conversion. Have you done any simulation earlier or any experiment?
Then we had just quantitatively checked in the lab that a differential input, that a circuit, differential circuit gives some gain, which when we apply the same voltage at the gate, but we did not like quantify it or like measure exactly the CMRR. We just have to check in the lab that it is not perfect exactly.
Yes. So all of you might have observed this, that okay, means even if you're applying same common mode signal, output will be different, right? So that experiment you must have done. Everybody has done that. Any doubt in that? The third amplifier. What is the scenario? So we have basically single-ended input, sorry, single-ended output. So in this case, output is single-ended. Therefore, it is not having the benefit of cancelling out, right? So we are not taking V out plus minus V out minus. We are having a single-ended output. But still, this amplifier gives good common mode rejection. Why? Because if you are applying, suppose, the same common mode, delta VG on both of them, same. For the common mode case, what is the effect of this? So this will produce some, assuming that it is going to produce some small signal current. So whatever small signal current it is producing, suppose it is I, delta I. So this delta I goes here. It also mirrors and goes here, delta I, because it is acting like a current mirror. And this guy is also producing the same delta I. Now in this case, this delta I are in the same direction, right? Earlier it was summing up. Now it is subtracting. Therefore, if I assume an RO, nothing is going inside it ideally. Is that clear? So this mirroring effect is trying to cancel out the common mode disturbance. So whatever common mode current is being produced by the M1, M2 is trying to cancel it out, because M1 small signal current is getting mirrored by M3 to M4, and then the M2 and M4 currents are in the opposite direction and they're canceling it out. Therefore, despite having a single-ended output, this topology, although it provides finite common mode ejection, but it has good common mode ejection. Is that clear to everyone?
Yes, sir.
Ideally, of course, we will get finite common mode ejection if I look at single-ended output divided by differential input. But still, because of this cancelling operation, we get a decent common mode ejection. So these three amplifiers you should be very conversant with. And the second amplifier, what is the problem the second amplifier has in terms of DC bias? So the first amplifier output DC bias is how much?
So it is equal to the output DC voltage because it's layout connected.
How do you define the output DC bias in the first case? Yes, given this circuit, how will you estimate the output DC bias of the first case? Quickly. What is the big deal? Means what will decide what is output DC bias?
Sir, it will be
Like the
given by
current flowing
VDD
through, right?
minus VSG2.
VSG2, right? So because ultimately you are feeding some bias IB by 2, and that IB by 2 will decide what is the VSG2. So VSG2 will decided by ID by 2 and W by L. Whatever W by L you put here, according to that, you can calculate the VSG. Ignoring the channel length modulation, you can calculate what is the VSG required to support the ID by 2. So in this case, output DC point is well defined. We can calculate. In the third case, how do you calculate the output DC point? Yes, in the third case, how do you calculate the output DC point? Yes, any response? Quickly, fast. Yes. These easy things you should be able to tell. What is the output DC point? How do you calculate the output DC point for the third case? I'm not hearing anything.
Sir, that the current will divide into equal parts, right? So the left part is direct connected. So that determines the gate voltage of the left PMOS, and since they are connected, so the rightmost gate voltage is also fixed by that. And then the current which flows to the left one is same as the current which flows to the right one. So then if we write the current equation, then that will determine the VDS, right? The the saturation equation.
Yes,
The
so
one
that is
plus
correct.
lambda
So
VDS.
because here, if I assume that the VG of the input devices are same, that the devices are well matched, then you have the VGS, VGS1, VGS2 are going to be same, and you are going to get the same current in the two devices, assuming that we are ignoring the channel length modulation. Channel length modulation can be ignored provided the lengths are significantly big and we are not using minimum length transistor. And in general, analog circuits, even if we work on advanced nodes, we use larger channel length. So in inverter and digital circuits, we use minimum length, right? But analog circuits, because uh, we need good gain, we need RO. So generally, we will use larger length. Therefore, this approximation that okay means we can ignore the channel length modulation can be still approximately valid. So assuming that we ignore the channel length modulation, uh, if I have the gate voltage of the input device is same and I bias is provided over here, it will take IB by 2, IB by 2, right? Each of them will take IB by 2. And then the same IB by 2 is flowing in these two devices. And as a result, it will develop some VSG, VSG3. And this VSG3 is same for VSG4. And now these two devices are also carrying same current, and VSG3 is also applicable for the M4. And as a result, the VDS of M4 or VSD of M4 should also be same as VSD3. And as a result, output DC point will be same as whatever DC point you have at this node, this particular node. So in this case, the output DC point is once again decided by the bias current and the W by L of M3, M4, because VSG will depend upon bias current of this M3 and the W by L of M3, M4. Is that clear? What about the middle case, second case? Second case, what is the problem? If you have seen in the lecture, I might have
So
discussed.
in the second case, since the upper two MOS are biased independently with a different DC voltage, not different, I mean, they are the DC voltage used to bias the upper pair and the lower pair are different. So there might be current mismatches in this same branch, which will lead to one of the MOSes going out of the saturation mode. So that's why it may lead to drastic changes in the output DC point.
So this is your VG CM, VGCM. This is your VB, whatever you call it, VB2, VB1. So in this case, you have some I bias and you are setting some VGCM for this. And assuming that the lower MOSFETs are fully matched, and we are, in this case, the problem is how do you calculate what is the equation that we write for the output voltage, output DC voltage? What does it depend upon? In remember the previous case, we ignore the lambda. Why did we ignore the lambda? In this case, we said that, okay, we will ignore the lambda. Ultimately, this problem is given that, okay, some I bias by 2 is flowing. You find out what is the VGS across this or the gate voltage across this. The ideal equation, the complete equation in saturation region is 1 upon 2 mu n COX W by L, VGS minus VT square 1 plus lambda VSD. Now again, you can just reverse this VSG rather than, so, I can just, for the sake of, clarity, I can just, and this is your mod VT, VSG minus mod VT. So this is the exact equation, right? Now, in this case, we said that, okay, you ignore lambda. Why are we ignoring lambda?
Sir, because quadratic dependency is more than linear dependency.
Sorry? Once again?
Sir, because
Can
the
you repeat?
quadratic dependency is there for VSD, so it clearly has greater effect than the linear dependency on VSD.
Not only that, the magnitude, right? So here, what is the unknown? Unknown is the VSG. The gate voltage is the unknown. So in this case, if you look at the unknown, source is anyway known. So VDD, VSG. So VDD minus VG minus mod VT square 1 plus lambda P VSD. So VDD minus VG, because the source and the gate are, the drain and the gate are same. So VDD minus VG. This is the equation. And in this case, what is the value of lambda generally that we have seen? What is the value of lambda? 1 plus 0.01 something. So you have basically, VDD minus VG. So X minus mod VT, whatever. So X minus mod VT square and 1 plus 0.01 X. So as compared to the first term, second term is definitely going to be much smaller, right? I can ignore the 0.01 X. Is that clear? We put the numbers, right? The number range also, it depends on what range X is. If X is very big, then you cannot ignore. But if X is, in this second bracket, 1 plus 0.01 X, what is X? X is, in this technology, we are talking about the VG. So it may be less than, say, 1 volt, somewhere around 0.7, 0.6, something like that, 0.6, right? So this is something like 1 plus 0.06, 006, something like this, right? So this, as compared to 1, can be ignored. Is that clear? So then, in this case, it is okay to, ignore. But in this case, it is not okay to ignore. Why it is not okay to ignore? Because you have to find the output voltage, output DC V out. VG1, VG of the both transistors are fixed. VG of the upper transistor is also fixed. So these are not variables. These are fixed. The only variable is the output voltage, drain voltage. And we want to find out that voltage. Therefore, we can't ignore the lambda, because lambda is going to lead to the drain voltage, because the output voltage in this case is dependent upon lambda. Is that clear? My known variables are VG, CM, VB1, VB2. These are known variables. Unknown variable is V out, the drain voltage. So calculating, what will you do? You will ultimately equate the current in the two devices, right? ID1, whatever you call it M1, you can call it M3. We will call I1 equal to I3. And then calculate the output voltage. So I1 equal to I3 equal to, assume that we are having IB by 2. So both are equal to IB by 2. I1 is given by VGS1 is VT square, VGS1 minus VT square. Now this is a constant, right? 1 plus lambda VDS. So VDS is V out minus VS, whatever you have. That is also you can, for the time being, assume that this voltage is some DC voltage VS, minus VS square. 1 plus this, and this should be equal to the upper side. So for that also the same, you have to write some K constant will come, some K1 VSG. So VSG minus mod VT. This again is constant times 1 plus lambda P. This is lambda N. So again, for this one, it is lambda P times VSD, right? So what is VSD? VDD minus V out. So this is a constant term in this case. This is a constant term. I can forget about this. So now my V out is dependent upon 1 plus lambda N V out minus VS. I'm just, some constant K, K1, K2. So I can take it on one side and put it as a K effective or some ratio. 1 plus lambda P VDD minus V out. So in this V out equation, ultimately you will get a strong dependency on lambda N and lambda P, right? Is that clear? The V out expression is solely dependent upon this lambda and lambda P. Other values are all constant. So lambda and lambda P will have a strong dependency on this lambda and lambda P. These lambda and lambda P are going to vary a lot from device to device. You have seen in the exam also, sorry, in your lab also, the different devices will have very different values of, the lambda. So for the MOSFET, you will get very, very different values of the slope. So lambdas are going to be significantly different. As a result, the output is going to be very, very sensitive to the lambda. And as a result, it is not well defined. If you design 10 such differential amplifiers, after fabrication, the output voltage will be, it will be strongly dependent on lambda and it will vary a lot. And especially if you are trying to bias it in the high gain region. So differential amplifier also has a input output characteristics, right? So, if it will also have V, if this is the differential out input, V in plus minus V in minus, ultimately, how does the output look like? Output curve will be like this, right? So you have seen this kind of curve. This is your V out plus, and this is maybe V out minus, and this is your x-axis is V in plus minus V in minus. So in this case, if this region is very narrow, right, this is the high gain region. And as a result, first of all, your output DC level is very highly sensitive to the lambda. So you may end up anywhere, here. So in this high slope region, because of small changes in lambda, you may end up anywhere in this curve. So it may end up, one of the side may end up being close to ground, another side may end up being close to VDD. Is that clear? So this is not a self-biased circuit. It requires additional help for biasing. So fully differential amplifier with current source active load. This is called current source active load. So in this case, it is not self-biased and it requires an additional circuit called common mode feedback for biasing. Whereas the other two schemes are self-biased. Is this clear to all of you? How many people are still there from EE? EE people, can you raise your hand? EE people? So there are only 3 people from EE right now. Okay. Five people from EE and rest. So EE, we have to, encourage more people. So somehow, anyway, today, half the people are absent anyway. So any question before? So we have already spent good amount of time. So rather than going into the OPAMP directly today, I will give you some assignment based on DFAM first. Those who are not clear with it, they will get comfortable after simulating the DFAM. And then tomorrow we will discuss some OPAMP schemes. Any question before we conclude? Put down your hands. Any question before we conclude? But this one is again like a recap. Yes, any question?
So one thing which I wanted to ask is that, like in this topology which you discussed, the current source topology, if the current, there may come cases, right, that the current which is flowing through a single branch, the DC current, is getting mismatched. Like the current in the NMOS is different from the current in the PMOS.
Which case? The mismatch analysis.
Yeah, mismatch. Third case mismatch. No, not third case. I mean second amplifier mismatch.
Yes. So second amplifier, what is the problem?
The problem, sir, what I wanted to ask is that if it because of mismatch, if it occurs, that the current which is flowing in the PMOS is different from the current flowing in the NMOS slightly, then what will happen to the output voltage?
Current in the PMOS and NMOS cannot be different, right? So current in the PMOS and NMOS will be same. In the two branches, you can have different current.
What I meant was that assuming that they are in saturation, the currents are coming out to be different. So how
current cannot come out to be different. As long as the devices are in series, the current will be same.
Okay, sir.
In one branch, current cannot be different, right? They are series connected devices. So whatever current is flowing in PMOS, the same will flow in NMOS. Only thing is the two sides you can have different currents if the mismatch is there.
Yeah. Yes, sir. But my query was that what I wanted to ask is that suppose we assume that both devices are in saturation and then we write the current equation and then equate them. But it does not have a solution. That indicates that in saturation, both of them cannot have the same current, right? So one of them must go out of saturation. Then how will I
What
understand
do you
that
mean?
which
So
one
this
goes out of
equation is for, so this is whatever I have written is for saturation region only, right? And it is solvable.
Yeah.
What is the problem?
Like, sir, because I was simulating this thing in the LT Spice, and it showed that one of my MOS is getting out of saturation and getting in triode. That's why I am asking the thing. Hello. Hello. Hello.
I think the call dropped in between. So could you listen to the discussion that I gave just now? Who had asked the last question?
Hello, sir. Can you hear me?
Yes.
Hello. Yeah,
Yes, I
sir.
can hear you.
What I wanted to ask. Yeah. Sir, what I wanted to ask is that I simulated one of the circuits in LD Spice, and then it showed that one of the MOS is in saturation. Like, I do not remember now exactly. I think the lower one or the upper one, one is saturation and the other one was in triode. That's why I was asking.
So whatever happens, the current will remain same, right? As long as the two devices are in series, the current will remain same.
Okay.
Whether one of them is in triode, both are in triode, one of them in saturation, doesn't matter. Because they are series connected, whatever current is flowing in one of them, the same DC current will flow in the other, as long as the DC current is concerned.
Okay.
While calculating this expression, this here we have assumed saturation region operation, because that is for the differential amplifier operation, that is what is desired. But as I mentioned, for any other condition also, I1 will be equal to I3. There is no change in that. Is that clear?
Yes.
Anybody else, any questions?
Sir, I had a question about the CMOS inverter. Sir, like when you discussed about its use as an amplifier, so in a normal amplifier, what we see is that in the low frequency region, the gain is almost constant, and then after the first pole, it drops down. But sir, in this case, like you said, that it acts as a high pass filter initially. So that I understood, but why does the gain fall off after and after the second pole? That I could not understand.
Second pole, so the second pole will come because of the high frequency poles, right? So one is the high pass pole and second is the low pass pole. So here you have some parasitic capacitance, CP. Even if you don't have any load capacitance, you have parasitic capacitance, and you have some small signal resistance. So here, if you look at the RF, you have the Wien signal. If you break the RF into Miller, you will get some equivalent. You can break it into an equivalent RL over here by Miller. Now this is the effective Miller resistance over here, and then you have the MOSFET. So now you have a common source amplifier with a RC load. So any common source amplifier with RC load will have a high frequency pole. So what is the doubt in that? One is the low frequency pole, which is basically because of the coupling capacitor and the RF. Because here, if you break RF into Miller, you will get some R in over here, R in by Miller. And then this is a high pass section. Whereas if you look at this part, this is a low pass section. You are loading the ideal amplifier with the RC load. The amplifier itself has its own parasitic capacitances and resistances, and along with that, this effective RF is also contributing to the output resistance. So this is a low pass pole.
And sir, another thing which I could not understand was how this R affects the bandwidth, because I think like if this R increases, then this 1 by RC goes down, so the bandwidth should increase, right?
Yes, that's we discussed, right? So your this side, if your R is increased, this one will come closer to the origin.
So sir, in this case, gain and bandwidth can increase together, right? Because when this R increases, this gain also increases.
So the gain is, here we are talking about the gain in this case will be determined by mostly the GM RO of the device. Once your R is large, and RF stops playing any further role in the gain. And then your bandwidth lower side, you are just, high pass side bandwidth is improving. So you can say yes, means in the lower cutoff frequency is going pushed towards the origin, but the bandwidth generally is defined in terms of the higher one. So lower side anyway, it is good to push it from maybe 10 hertz. You are able to push it to 1 hertz. You are push it to 0.1 hertz. But how fast you can operate the circuit, that will be determined by the upper pole. There you have again the same constraint. This will not decide how fast you can operate the circuit. This will just decide what is the minimum signal you can pass. But when we talk about bandwidth and the speed of the circuit, more often we are concerned with the speed. That speed is determined by this. Is that clear?
Yes, sir.
Any other question? Any other question? Yeah, in none of the simulations, I saw this amplifier. Everybody did only the inverter. Amplifier I did not see. I had given question on amplifier also, right? Or not? Oh, I did not give a question on amplifier. I forgot to give. Okay. So somehow I think I missed it. All right. Anyway, so I will give you some small assignment on the differential amplifier, and tomorrow we will cover op-amp. Any question before we conclude? Any question before we conclude? If not, let us stop the recording. Stop recording. And